And so this first one, we have y is directly proportional. So whenever you're directly, it's just kind of multiplying. Y is directly proportional to the square of it. So that's how that equation would look like translated. That second one, y varies inversely. That's your clue, you have a denominator. It varies inversely with the product of x and 1 minus x. Again, we won't really be looking at problems like that in this class. This is calculus, and there's not really a derivative there. Ones that we're going to be looking at will be ones like what's at the bottom of the page. So this first one, I have y prime is directly proportional to the sum of x and y. So what would that equation look like? I have y prime is directly proportional to the sum of x and y. How would we probably look at that in this unit? Y prime, we know, is the derivative, so this is technically a differential equation. So you could have written it as dy dx is directly proportional to the sum of x and y. Wouldn't be able to solve that one. That one's not a separable differential equation, but you could do things maybe like Euler's method. You could do things like find a slope field, interpret a slope field, find a tangent line, find the concavity. We can still analyze that, but we wouldn't be able to solve that problem. The second one would be one that we can kind of solve. So I have the rate of change with y with respect to x. So all that is basically just telling you dy dx. And dy dx, it varies jointly as x and the reciprocal of y. And that's how we translate that one into a statement. Probably condense it a little bit and write it as dy dx is equal to like kx over y. That would be one that you can solve pretty easy, that you can visualize multiplying both sides by y and dx and then integrating both sides. So that's the first thing that you're going to do with a lot of these problems, is just kind of read through them and be able to set up the equation that's being described. The second thing that I want to talk about before we get to the word problems is different types of equivalent answers we can find. So this first one, I have y changes at a rate that is directly proportional to the square of x. We already just did this one on the previous slide. But I changed it, so now I'm saying that y changes at a rate. So that is referring to a derivative now. Y is changing at a rate, that would be y prime, that is directly proportional to the square of x. This one, again, a pretty easy one to solve, but we want to talk about like equivalent answers. Instead of y prime, we could have also written this as dy dx, of course. Either way, we don't really need to worry about separating the variables too much, because there isn't really just a y term in there. So we know that when I separate it, move that dx the other side, and then integrate it. What is that going to give us? It will give us the general solution. So y would be equal to, k is a coefficient, x cubed divided by the new exponent plus 3. That would be the general solution to that specific differential equation from that description. Now, often for these, if we want to have some sort of general solution, we want to sometimes make that as like simple and easy to deal with as possible. We've done this before with some problems, but we have this k. Again, what is k? It's some number. It represents the constant of proportionality. You could plug in initial conditions here if you had them, solve for k and c. Or another way, just looking for a general form, if k is a constant, what is k divided by 3? Just another constant. So you can write it as y is equal to, we'll choose f, x cubed plus c. It could be any letter, just choosing a random one. Those two equations would be then like identical. Like they would have the same slope field, they would have the same kind of values if you solved it. You would just want to kind of keep track of like when you plug your initial condition and what you're solving for. I will say when we get there, a lot of these problems you're going to have two initial conditions because you have two unknowns. You have the constant of proportionality, and then you also have the plus c. So there usually will be more than one initial condition, and you usually have to solve. It takes a little bit more time to solve, but basic algebra. Here's another one that I want to look at. So I have y changes at a rate that is directly proportional to the square of y. So again, y changes at a rate, we know that's the derivative. I have dy dx is equal to, it is directly proportional to not the square root of y, to the square of y. That's the differential equation. Again, oftentimes we're going to think of like, there's the differential equation, then there's the solution. Don't have an initial condition, but we can find the general solution. Separating your variables, I'm going to move my y over to the left-hand side. And so that's going to become y to the negative 2 dy is equal to k dx. Integrating both sides, that's going to become y to the negative first with a negative 1 in front. K is just a number, so what's the integral of k going to give you? Kx. And then, of course, don't forget your plus c. And then we're going to go ahead and solve it for y. So the integral of k becomes kx plus c. And then we have different options for showing equivalent answers. That's why I chose this one. I can think of at least 3 different equivalent answers we can write for this one. I might first divide everything by a negative. So that's going to become negative kx minus c. Y to the negative first is 1 over y. To solve for y, you can think about cross multiplying, or the easier way to make kind of one step. If 1 over y is equal to all that, then just do the reciprocal, and we know that y would be equal to 1 over all that we had. That is one general solution that we have. Again, we like talking about like equivalent general solutions. You could imagine factoring out that negative 1 in the denominator. If I factor out that negative 1 in the denominator, then I have the general solution of negative 1 over kx plus c. Again, that is a valid and equivalent answer. Other equivalent answers I could come up with is, so I have k. K is a number. What is negative k going to be? Just another number. K is a number. Negative k is another number. As long as we don't know what it is, I can just kind of plop in whatever letter I want. I'll do C, D, X. Same thing here. What's negative C? If C is a constant, negative C is also a constant. Let's rename it, and I'll name it E. Technically, all 3 of those, the one I have in the black ink, the purple ink, and the green ink, all 3 of those solve that differential equation. Why do I do that? We often just kind of want to deal with like a simple general solution, but as long as you're consistent, so like if you were going to plug in an initial condition to like that first one in black, know that you would be solving for k and c in that form. If you rewrote it, so say if I rewrote it into the green equation, and then plugged in my initial condition, I'll be solving for D and E, and I want to make sure I plug it into that version of the equation. But I think it's nice to look at these and just talk about like, how do we recognize equivalent answers? Any questions so far before we move into the word problems? All right, so how I have the word problem set up is I have 4 of them. We're probably just going to get done 2 of them today. But basically for each word problem, you can kind of see for the most part, I have the question with a multiple choice matching. I have a slide where we're going to actually solve it, and then basically a follow-up question that will answer using what we find. And I have 3 examples, like a bacteria one, which is a pretty common one dealing with decibels, one dealing with an apple falling, and one dealing with a balloon being inflated. So on the first part, the first thing I want to do is, if we have a question we're presented as, that we can read that question, that we can first write the differential equation that's being described, and then we can also, without solving it, or maybe thinking about what it would look like after being solved, which slope field would be the best match for that problem. So here's the bacteria. I have y of x represents the population of bacteria. So it is important to represent that y is representing a population in millions on day x. So y is the population, x is representing the time, and it's going to be measured in days. We have y prime varies directly as the current population. So that statement is what's going to give us our equation. And then since we often have two initial conditions, or excuse me, because we have two variables, the constant of proportionality, and then often the plus c after integrating, we do have to have kind of like two initial conditions to eventually solve this one. So we want to first figure out which slope field matches this. I think if you were stuck and you're like, I don't know what that equation looks like, it's pretty easy to plot some points and figure out which one matches. So like it does tell me that at x is equal to 0, there's 3 million bacteria. So here's the initial condition drawn on all the graphs. And then at x is equal to 4, there's 5 million bacteria. So there's the two initial conditions on those slope fields. Which initial conditions can we easiest eliminate, most easily? C and D. So we see that this population is growing. It goes from 3 million to 5 million. So we can go ahead and eliminate C and D. Both of those have slope fields that are decreasing. So now we are deciding between A and B. Which one appears to be the best fit for that data? B. And I would argue that B looks the best. Again, you can kind of draw A is flattened out pretty fast. B pretty much hits it automatically. Say it was harder to tell, you can kind of think about what the differential equation looks like. So let's write the differential equation. It says y prime varies directly as the current population. So it is going to be k times something. Is it going to be k times x, or is it going to be k times y? K times y. So it's varying directly as the current population. Well, what variable is representing the population? The y. So it is k times y. Y prime is the same thing as dy dx, which is then, of course, equal to k times y. Without solving it too much, like you can imagine, I'm going to have to divide by y, so I'll have 1 over y. When I integrate that, that'll become the natural log of y. How do I get rid of a natural log? Take the e of both sides, which will turn it into an exponential. So which graph is the exponential? The answer is definitely B. Now we are going to solve this one, and that will make that choice also just as obvious. But one thing I want to be able to do is, like, when we have a situation, being able to kind of see which slope field matches what's being described. So let's go ahead and solve this problem. And so I'm going to go ahead and rewrite my differential equation. So I have dy dx is equal to k times y. Let's go ahead and solve it. Separate the variables. I have 1 over y dy is equal to k dx. Take the integral of both sides. That's the natural log of the absolute value of y, which is equal to kx plus c. Some things we can kind of notice. Do I technically need to have the absolute value on the y for this particular problem? No, we're not going to have negative bacteria, and that's going to be true for a lot of the word problems. It's like it's going to be positive no matter what. So let's think about how we would end up solving this for y. We are going to have to do the base e of both sides. Again, I can drop off the absolute value because we know that y is going to be always greater than or equal to 0. We have a positive population. So this becomes y is equal to e to the kx plus c. And all of that ends up being in the exponent. I do want to pause right here and kind of talk about why I'm solving for y now. Typically, I always plug in my initial condition first and then solve for y. For a problem like this, where we do have two unknowns, we have both the k and the c, it's often easier to solve for y first. It just makes the algebra in the long run a little bit easier. I'm also solving for y because I want you to see what type of graph this is going to become. So I do have this y is equal to kx, and let's just talk about how we can simplify this, because that is kind of a long exponent, it's kind of a gross exponent. Well, we do have some properties of exponents. If you're adding inside the exponent, how can you split that up? Multiplication. So this is the same thing as saying y is equal to e to the kx times e to the c. Well, c is a constant. We don't know what it is yet, but it is a constant. What is e to the c going to be? just another constant. So I'm going to rewrite it as, I'll just choose d e to the kx. And again, we're saying that e to the c is just another constant. Does anyone recognize that exponential equation we just got? It's the PERT formula you might remember from Algebra 2. You probably look at it more like this. P of t is equal to the initial population of e to the r times t. I think most of you have seen that from Algebra 2, or at least you should. I know you have. That is where that formula comes from. And that is a really important formula. And that's where we're going to make some connections at. And so here's a shortcut you'll love. This differential equation up here, this is the exponential growth or decay differential equation. It is the most common differential equation we have when we're solving these word problems. So whenever you see that, you know automatically whatever is being described as growing exponentially. So if you ever see that, you can jump straight to this general solution without showing any work. That is allowed in the AP exam. I recommend it. You can jump straight to that answer without showing any work, because we now know k times y, and it does have to be y, not like t or x. So it has to be with the dependent variable. dy dx of ky is the exponential growth differential equation. Don't worry about separating, don't worry about integrating, just jump straight to that exponential growth form. Why is that exponential growth form nice? Is because then it does make it pretty easy to solve. So if we jump straight to this answer, it does give us two initial conditions. At 0, there's 3 million bacteria. Let's plug in that initial condition. So 3 would be equal to d e to the k times 0. Well, k times 0 is 0. E to the 0th power is 1. So we know that d is equal to 3. Then they give us another initial condition. It was at 4, there are 5 million bacteria. So 5 would be equal to this 3e to the k times 4. And then we do just want to kind of use our algebra skills now to solve for k. So algebraically, how we're going to solve for k, definitely want to have strong algebra skills kind of with these topics. I'm going to divide both sides by 3 first. So that's, of course, 5/3 is equal to e to the 4k. I'm solving for k, so what I need to do next algebraically, take the natural log of both sides. So I would have the natural log of 5/3 is equal to 4k. So k is equal to 1/4 natural log of 5/3. So now we just want to go ahead and plug it into that equation. What was that general form? Y is equal to d e to the kx. So I have y is equal to, d was 3, e to the k times x. And that would be your particular solution. If this was the AP exam, do you think that would be one of the choices you would have? You know well enough if I'm asking, that's definitely not the choice that they would leave. It's also like not a friendly equation to use. Like there's an e there and a natural log there. But by seeing an e and a natural log, we know that eventually those should cancel out. So how can we make those cancel out? Well, we just need to rewrite it. We know that the order doesn't matter when you're multiplying. So I'm going to have 3e, 1/4 times the natural log times x. Doesn't matter which order you multiply as long as you're multiplying. So I'm going to move the natural log first times 1/4 of x. And then what we can do is use another exponent rule. I know that if I have a to the b raised to the c, power to a power, what do you do with the powers? Multiply. So we can also go in reverse. Those exponents are all multiplied, so I'm just going to think about grouping that piece together. Well, what is e to the natural log of 5/3 going to give you? Just 5/3. So your final equation would just be y is equal to 3 of 5/3 to the 1/4 of x, which looks very much like an exponential growth problem. We know it's a growth problem because 5/3 is bigger than 1. So again, after you do that step, there really isn't a lot of calculus. And to be quite honest, I'm going to kind of zoom out, I guess, to show it. This problem you can pretty much do entirely without calculus as long as you have memorized that whenever you see dy dx is equal to ky, that you're going to jump straight to that form of a solution. And then it's basically an algebra 2 problem and no longer a calculus problem. Yes, sir?
Would negatives matter?
The negatives will still kind of show up if necessary with your initial conditions. But for these, it's going to be decay. So what will end up happening is you would have a number less than 1 in that final parentheses. All right, so how can we use this? We know this is a calculus class. Like, so far, you could do that problem without the calculus as long as you knew that fact that dy dx equal to ky gave you that kind of shortened solution. I try to come up with the notes just like a variety of follow-up questions. So the first one I have is, at what rate is the colony's population growing when x is equal to 8? So when you see that, if you want to kind of make sure you're answering the question that is being asked, if it's asking at what rate is the population growing, is it asking for y or dy dx? It's asking for dy dx. So it's at what rate? It is asking for a derivative. We know that a derivative is a rate. Well, what is dy dx? Dy dx is k times y. Well, we already found k. What was that k? K was that 1/4 natural log of 5/3 times y. But then we have to look at this and be like, oh man, we're trying to find the rate when x is equal to 8, but this derivative is in terms of y. But do we know what y is? Yeah, we just spent all that time solving for it. What was y? Y was equal to that 5/3, the 1/4 of x. So I can plug that in. So what is dy dx? Dy dx is your k value, which we had to solve for, times what y is equal to, which we found. And we're trying to find the rate when x is equal to 8. I'm not going to bother simplifying that. Like, this would be like a calculator problem. You can type it in at some decimal. But this would be the rate we have. Does ask us to include units. What would be the units of that? Millions of bacteria per what? Per day. So again, like, we're just using what we found to kind of plug in all those values and answer. Biggest mistake I see, people know that dy dx is ky. They know they found k, and then they just make the mistake of trying to plug 8 in for y. But we had to use that 8 to find the y and then plug it in. What about this one? This was kind of a algebra 2 problem. How long does it take for the population to double? What equation can you write to figure out how long it's going to take for the population to double? What was the initial population? 3. If it's going to double, what's it going to turn into? 6. And you're like, well, isn't that just for one kind of doubling time? And you're like, well, this is still a differential equation. It is a constant of proportionality, so like that rate is still going to be a constant. So if the initial condition was 3, like we knew that at 3, it will double when it would reach 6. So then we can just solve this. And again, at this point, the calculus is really over. We just need to know how to solve this algebraically. Solving algebraically, divide by 3 first. So I have 2 is equal to the 5/3 of 1/4 of x. And then reviewing those algebra skills I hope you have, what would you have to do next algebraically to start solving for x? You would take like the log base 5/3 of both sides. That could work. So you want that 5/3 to cancel out. That'll become the log of base 5/3 of 2 is equal to 1/4 of x. And then multiply by 4. So x would be equal to 4 log of 5/3 of 2. The other way to solve it, some people don't like doing a log-based 5/3. Another way to do it is you can still just take the natural log of both sides. Like you can always take the natural log of both sides. And how that is useful, if you take the natural log of both sides, that 1/4 of x is in the exponent. What can you do with exponents? Bring it down in front. So this becomes the natural log of 2 is equal to 1/4 of x times the natural log of 5/3. Divide, multiply by 4, so we get x is equal to 4 natural log of 2 over the natural log of 5/3. And you might be saying, wait, Mr. Brown, those two answers are not the same. And I would argue that they're actually completely the same and identical. How can we get them the same? I can use the change of base formula. The change of base formula states if you have a log of base b of c, that's the same thing of log base a of c over log base a of
That was in my
b.
mind.
In your mind, right? Change of base formula. This is the same thing as 4 natural log of 2 over the natural log of 5/3. And if you're feeling really fancy, because I know you are, you're just like, Mr. Brown, just show me all the ways you can rewrite this problem. That denominator is the natural log of 5/3. That's a quotient inside of a logarithm. You could have written that as 4 natural log of 2 over the natural log of 5 minus the natural log of 3. Any other ways you can think about rewriting that one? Oh, I'm going to keep going.
Factor of.
What can I do with that 4 in front? Put it to the top. So I could write it as the natural log to the 4th is 16 over the natural log of 5 minus the natural log of 3.
That's exactly what I had. That's so weird.
So yeah, you need to know your log rules. This is just a taste of what's to come. So just so you know, that is a taste of log problems that we need to know. All those properties are going to be showing up in these problems. Where would they show up at? Let's look at our last example for the day. Here is one dealing with decibels. So I have y of x is representing the loudness of sound measured in decibels. And at a distance of x meters from the source, y changes at a rate that is inversely proportional to x. So we could use that to write our differential equation. And then for all these, we're going to have 2 initial conditions. And I say at a distance of 4, the loudness is 70. And then 8 meters from the source, the sound is 64. So first for me, look at that and see if you can find the differential equation that matches the two. I will say I don't reuse them, so we already used B for that first one. So there's just 3 options to choose from. See if you can figure out which slope field that matches to. And then we will solve this one, which will also have a lot of algebra that you want to kind of. And we have at a distance of, I'm going to go ahead and draw it. 4 would be 70. We're counting that y-axis by 10. And at 8, it's 64. 4 is at 70. 4 is at 70. 8 is at 64. 8 is at 64. Which slope field appears to be the best match for this situation? Or I'll say this way, which one can you rule out automatically? A, right? It's a decreasing description, so we can rule out A, because A's are all like increasing if you try to draw it in. So we're going to rule out A. And then we are deciding basically between C and D. If I'm just looking at the slope fields, C's is pretty steep. It looks like he misses that point, where D is decreasing but levels off a lot less. So it is going to be D. D is the one that matches to that. Let's go ahead and write that differential equation and solve it. So I'm going to zoom out because this one will need some more space. Let's write our differential equation first. Y changes at a rate, so that's going to be dy dx. That is inversely proportional to x. So that would have k over x. This one's a really easy to solve. Multiply by dx and then integrate both sides. Do want to kind of ask this one, is this one our special one that we can memorize and use the exponential trick? No, that only works when you have k times y. That's clearly, there's not even a y, so that's not an exponential one. Integrating it, we have y would be equal to k on the natural log of the absolute value of x plus c. And again, don't forget that c, these will always have two constants. 1 over x will be the natural log of x. Do I technically need the absolute value for this one? Guys, hush. No, like the distance was always positive, so technically we could drop the absolute value. So if I'm looking at this one, like I'm not going to really rewrite it. Y is already by itself, so there's nothing to really rewrite. What already can you tell is going to make this one a little bit difficult to solve for those constants? What's going to make those initial conditions harder to deal with? Let's see then. So at a distance of 4, the loudness is 70. At a distance of 8, the loudness is 64. Plugging those in, I would have 70 is equal to k natural log of 4 plus c. This bottom one I have 64 is equal to k natural log of 8 plus c. What's going to make that hard to solve for either k or x? Besides that, can you tell me immediately what k or c is? No, nothing cancels. Like it's not like 0 where something will cancel, or for a natural log it's nothing like 1, nothing's canceling. So what makes this harder is we have two equations and two variables. How have you learned how to solve a system of equations? So we have substitution, we also have elimination. My favorite for these problems is elimination, since the problems are pretty much identical. You can just multiply by -1 or just subtract one from the other. So I'm going to do elimination, and that's typically my choice for these problems. Because if we do elimination, what variable automatically is going to cancel out? The c. So I'm going to go ahead and subtract it. 70 minus 64 gives me 6. And so then I have k times the natural log of 4 minus k times the natural log of 8. Those c's were eliminated. Now we just have one equation, one variable, so we do want to solve for k. So 6 is equal to, I'll factor out that k, and then solve for it. Maybe to combine it a little bit, what's the same thing as saying the natural log of 4 minus the natural log of 8? Natural log of 1/2, 4 over 8. Could be real fancy and say the natural log of 1/2 is the same thing as negative natural log of 2, but we'll leave it as a natural log of 1/2 for now. Solving for k, I'm sure you're okay with that too. K is equal to 6 over the natural log of 1/2. Again, these problems tend to be more just like algebraic instead of calculus. Once you get to this point, like the calculus is over. The calculus stopped right here after you found the antiderivatives. The rest is just algebra. We know what k is. Now we want to find c. Does it matter which equation you plug it into? No, I'm going to choose the top one. I just think math is going to be easier with a 70 instead of a 64, just on like having to subtract stuff. Again, it wouldn't matter which one you did, but I have 70 is equal to k plus c. So k times the natural log of 4 plus c. So what is c equal to? C is equal to 70 minus the 6 over the natural log of 1/2 times the natural log of 4. Not a pretty looking c, but it's a c nonetheless. If you just want to leave an answer ugly, then our differential equation would be y is equal to, I have my k value times the natural log of x, plus the constant. That is a correct answer. Like if it was a free response question, you could leave it like that. Let's just talk about ways we can simplify it, just because we know those log rules are a thing that we probably need to review. Can use the change of base formula again right here. So whenever you're dividing a logarithm, you can use the change of base formula. This first term can be written as 6 log base 1/2 of x. Could have also become -6 log base 2 of x, kind of the same thing, plus a 70 minus 6 log base 1/2 of 4. Again, that's just me using the change of base formula. Does anyone see anything else you could probably simplify in that expression?
Log base 1/2 of x over 4.
So some options, you can maybe combine these as a single expression. So like you could factor out the 6 and then they are both logs to the base 1/2. I'm not going to do that because I want to review just evaluating logs. I think sometimes we forget how to evaluate them by hand. Log base 1/2 of 4 means 1/2 to some power is equal to 4. So I see the 2 there, like 2 squared is 4. How would I get the 2 out of the denominator? -2. So like this piece is just -2. So you could write this as 6 log base 1/2 of x plus 76 times -2 plus 12. And then of course add those together. Again, I could keep doing this probably for like 10 more minutes, just showing you different ways to rewrite it. I just want to emphasize, like, be familiar with your log rules, especially with multiple choice, that you're at least able to like find an answer that you could get with the one that you have. But to kind of focus on this, and I think what makes this unit, this topic easy, but then also difficult, is like literally the calculus stopped after the first step. Everything after that is you just doing the algebra, which is often where I see the mistakes at, not in calculus, but in the algebra. And looking at the time, I'm going to stop there. To Monday, we'll come together and we'll do the balloon problem and then the apple problem. And then it will basically be like a work day for the remainder of the day on Monday. The homework that I want you to do is homework number 4, and it's kind of some random problems in the book. But it's 11, 12, 19, 20, and then jump to 34 through 40 evens. Tuesday will be the last topic of the unit, which will be the logistic growth, which is going to be another memorized differential equation. Your test is on Friday, a week from today, and then that following Monday comes to class really ready to work hard for the next unit. That's going to be the series unit that we'll finally make it to. So yeah, last week of some gentle stuff, and then we'll get into the hard stuff after that. So if you want to stay behind and ask questions, you can. But if you're good to go, then I will see you next weekend for those of you who are at home. And yeah, that's it.